basic principles of mechanics. That is, exactly how is it that the mechanics that we're used to, whether it's your car going along a road or a railroad car going along the track, what is it that makes all those things function and how does it work? This guy thought very deeply about it. And in particular, his main concern was the origin of the concept of mass. Up until about the time of Newton, if somebody went down to the market to buy, say, an apple or something, they would usually weigh it in their hand. And whether it was good or bad, like a good potato or a rotten potato, an expert housewife could tell that by heaving it in her hand. The concept of density was a lot more immediate to people than the idea of mass. But it was Newton then that pointed out that the actual thing which causes gravity is not density, it's the mass of something, the mass per unit volume. It's a much more objective measure. So what Mach is basically remembered for is his philosophical studies of the origin of the concept of mass. Just how much of a certain material is there in a given space. And it's that which causes gravity, and it's that which therefore controls, to a large extent, the evolution of the universe. On the large scale, we don't think that the strong forces between particles, which are responsible, for example, for the structure of the proton, or the decay of something like uranium to lead, which involves a thing called the weak force, where an electron is emitted, a neutron, basically a proton, neutron decays to a proton and an electron, radioactivity, the weak force, and electromagnetism, which is the force between particles with opposite charges, but luckily for our universe, the numbers of the positive and negatives are just about equal. All of those three forces, for one reason or another, don't influence the large-scale structure of the universe. So to a good approximation, what we're left with is talking about mass as the origin of gravity. And most modern theories of the origin of the universe talk about mass and its evolution with time. This is an attempt on a slide to show you how Mach's ideas evolved through time. If you imagine in your brain something, a simple problem, like say the one I've got illustrated here, where you've got a spacecraft going around the Earth. I'll get to that in a few minutes, but there's basically a mass associated with the Earth. There's a mass associated with the spacecraft. The mass of the Earth attracts the mass of the spacecraft, okay? And because it's going in an orbit, the centrifugal force balances the gravitational force. By the way, in certain modern astronomy books, you will find them talking about something called the centripetal force, which is equal and opposite to the centrifugal force. And I've never understood why certain authors want to complicate life. It's actually the centrifugal force. When you get a stone at the end of a string and you whiz it around, you feel the force going outwards, don't you? The word centripetal means center seeking. Centrifugal means center fleeing. What you really got here is a balance between gravity and the centrifugal force, as in the good old-fashioned physics of when I went to school. So, the now question is, you've got the mass of the Earth and you've got the mass of this spacecraft, and they're in some kind of stable relationship to each other. There's a problem, which Mach pointed out. The mass of something like the Earth, which causes the gravitational field, if you want to kind of take it like that for now, should logically be called the gravitational mass. It's the thing which appears in Einstein's equations. The mass of the object that feels it should be called the inertial mass. It's the thing that, for example, if you throw some objects together and you get their kinetic energy out, like a baseball and a baseball bat, half mc squared, that is the inertial mass. Same as in E equals mc squared. The m is the inertial mass. You can take it for granted, because it's been written in books for hundreds of years, that the gravitational mass and the inertial mass are the same, but logically there's no reason why they should be. There's no reason why the measure of the thing that causes the gravitational field should be exactly equal to the mass which responds to it. Mark pointed this out and was therefore influential on Einstein, and he adopted the equality of the two kinds of mass and a thing called the equivalence principle. It has to be tested. Galileo did it, theoretically at any rate, by dropping objects off the Leaning Tower of Pisa, big ones and small ones, to see if they accelerated at the same rate. So what he's doing is to take things with big and small inertial masses and see if they accelerate downwards at the same rate in the Earth's gravitational field, knowing that the Earth's gravitational field is caused by the gravitational mass. Newton went better than that and looked at the motion of a pendulum. A complicated experiment, but very accurate, was invented by Erdős in about 1896. And in St. Louis, they've now got a much more refined version of this, and so have several other universities, basically because of the invention of the American physicist Dickey, who found a much more accurate way of doing that experiment. So whereas this one was quite primitive, this one with countervailing masses is a lot more accurate. To cut the long story short, the concept of inertial mass and gravitational mass are logically distinct, but they are in fact equal by measurement to about 1 part in 10 to the power 12. That is 1 part in a million million. So it has to be regarded as one of the most accurate experiments ever done in physics. Why they are exactly equal is still open to question, and I'll come to it. Anybody that does gravitation for a living, and I've been fortunate enough to be paid to do this throughout my life, will therefore wonder about, well, is this 1 part in a million million, is that it? Or is there some kind of breakdown of this? We can't, in fact, predict the future of the universe unless we know this law to better than that accuracy. So it's not just an academic question about verifying this. We need to verify it in order to have any kind of confidence in the laws that we're applying to the universe. So this is a conceptual diagram of a thing called a satellite test of the equivalence principle, wherein you put masses of different kind into orbit around the Earth aboard a spacecraft. And because you have masses with different kinds, different inertial masses, but they're all in the same gravitational pull of the Earth, that is subject to the same gravitational mass, you can figure out whether in fact inertial mass, being that which reacts to things or from which we get our energy, whether that mass is the same as the gravitational mass, which is what all of cosmology really talks about. Okay? As I say, we've got different models of the universe, and we need to know that equality very accurately. There are ways in which the universe can evolve, and they are given by Einstein's equations. On this diagram, what I've done is to plot a scale factor, which you can think of as being proportional to the distance between any two average galaxies in the universe, versus the time, where by convention we measure the time from 0. Some people put an R here, but in the really good textbooks you won't find them doing that, because if you write down a symbol R, it immediately brings into your mind the impression of a radius. And therefore, it also, for most people, brings into mind a distance from here to there, the idea of a boundary,